This conference will now be recorded.
The dog-bone-shaped specimen, for mold pressing, extruded filament was cut into shorter pieces to fit the mold. Then they were compression molded at a specific molding condition. This slide displays our interesting result. On the top of slide, you can see external microstructure obtained from SEM method. This figure shows cross-sectional image of polished surface of 3D printed sample. For observing precise SEM image, fracture surface was carefully polished and plasma etched. As can be seen in this microscope, 3D printed sample exhibit 3 separate components: matrix and fiber and void. However, these conventional microscopes provide only limited data, only for external microstructure, but give not sufficient information in internal microstructure. On the other hand, non-destructive X-ray microscope provide more meaningful image data than SEM method. By comparison, at the same region, you can clearly understand that X-ray microscope provide all the information for not only external microstructure, but also internal microstructure. This technology can easily visualize a 3D internal microstructure and can also quantitatively identify all the components as a segment of the composite through phase contrast. 3D printed composites show specific microstructure distinct from those of conventional composite. This figure clearly shows the distinctive architecture of each printed layer, where a bundle of filament is well-oriented parallel to a printing direction. All of the composite components, including fiber and matrix and void, all are highly oriented parallel to the printing direction. This phenomenon is closely related to high level of shear stress exerted on molten resin when it passing through the narrow printing nozzle. On the bottom of the slide, you can see how the fiber can be shear aligned from the narrow nozzle wall during 3D printing. This slide shows microscale tomographic research in both 3D printing and mold pressing. The effect of budget fiber loading content on internal microstructure, including fiber orientation and void distribution of the 3D printed samples, were comprehensively compared with those of mold process samples. As can be seen, image of 3D printed sample is shows slightly different in internal microstructure due to a difference in processing method. Bottom figure summarizes the result of comparing the component volume fraction between the 3D printed and mold process composite based on X-ray microscope data. As noted above, there is a significant difference in the trend of change in void volume fraction with fiber loading content between two groups. Especially in 3D printing, it was clearly observed that the higher budget fiber loading content, the smaller blue air gap between the layers was generated. This result means that budget fiber played an important role in the reduction of such unnecessary void. One reason is that budget fiber can effectively prevent dye swelling effect during 3D printing. Another important reason is related to high thermal conductivity of bidet fiber. It can give positive effect on void elimination. On the other hand, in mold process sample, the appearance of void was unpredictable, and void were randomly distributed throughout the polarimetry system. To define fiber position, length, and orientation inside the serpented composite, we conducted fiber characteristic study like this slide. This slide shows fiber length distribution before and after both serpenting and mold process. Initially, fiber length was broadly dispersed this range, but after fabricating the sample, severe fiber breakage occurred during both process. After that, the final length of the fiber embedded in matrix was about 100 micron or less. This figure also shows the research of the fiber orientation and indicate difference between 3D printed and mold process samples. 3D printed sample show almost all the fiber were highly oriented in Z direction, which is parallel to 3D printing direction. It means that the fiber were highly aligned in printing direction along the mat flow during 3D printing. On the contrary, mold process pressed sample show isotropically distributed fiber throughout the system. Surprisingly, the narrow nozzle of 3D printing induced markedly high fiber orientation of A33 value, H value equal to 0.8. These provide a high degree of anisotropy to the material. This contrasts with the transitional molding process, which exhibits a slightly fiber alignment in the resin flow direction, but it does not exceed A33 value up to 0.5. This difference between two processes can affect not only just fiber orientation, but also mechanical properties and friction behavior of the composite. The 3D images were quantitatively analyzed to verify the void formation mechanism via selective image segmentation. We specifically investigated the effect of bidet fiber on the void formation during 3D printing. As a result, totally different types of void were thoroughly observed throughout the entire step. First one is blue color intervoid, which can be formed between the interface between interfilament. The other one is green color inner void, which microsized and scattered throughout the composite. They can be formed due to the weak interface between fiber and matrix. The result showed that according to the bidet fiber, this blue color intervoid tended to gradually decrease, but some green color inner void newly formed. There is a trade-off relation between larger size intervoid and small size inner void according to the bidet fiber. Due to effect of high thermal conductivity of the rigid bidet fiber, the inner void can be effectively controlled and removed according to the violet fiber. However, in case of this green color inner void, it can be caused by weak interface adhesion between fiber matrix, and it became worse according to the fiber content. This slide shows the tensile strength of both 3D printed and mold process samples. The tensile strength of 3D printed samples followed similar trend on mold process sample according to the budget fiber content, but it is slightly different. This is due to the anisotropic mechanical behaviors based on their specific microstructure induced by process. Especially in terms of specific tensile strengths, one noticeable thing was that 3D printed sample was better than mold process sample at a certain budget fiber content. The specific strength is equivalent to the its strength divided by material density. 3D printed sample have higher void content, but show a decreasing trend with an increase of budget fiber content. Due to the presence of void, the density of 3D printed sample was lower than that of mold process sample. Overall, the specific strengths of both samples followed the same trend as tensile strengths. However, the 3D printed sample show a higher specific strength than mold process at a certain budget fiber content. This result is highly related to high-order fiber orientation and high-volume void content in 3D printing. In the next session, I will be discussed in detail. This slide is a description of the positive effect of high-order fiber orientation on the composite strength delivered from 3D printing. This graph shows the mechanical property prediction through the theoretical approach according to the rule of mixture. In both 3D printed and mold process composite, the theoretical tensile strength tends to increase linearly like this. Notably, the 3D printed composite initially show a relatively low tensile strength, but the value increased sharply with budget fiber content, eventually exceeding the mold process composite at this point. This is because the 3D printed composite have high order fiber orientation compared to tensile load direction. This induces a high level of shear stress between fiber matrix during tensile loading, which resulting in effective improvement in strength, because this stress can develop into plus stress, which represents a fiber strengthening mechanism. On the contrary, in case of void, it negatively affects mechanical properties. This graph shows that according to the budget fiber, blue color inner void tend to gradually decrease, but green color inner void tend to severe. In terms of fracture behavior, initial cracks can easily propagate through these numerous small inner void at the weak fiber matrix interface, rather than through the largest structural inner void present between filaments. This is because the inner void at the interface between fiber matrix lowers the load transfer from the matrix to fiber and act as a major crack path, thereby leading to the fluid fracture. On the other hand, intervoid, which is aligned in the tensile direction, can even block the crack propagation in a perpendicular direction to tensile load direction. So when compared to multi-process composite, it is a positive effect on the mechanical properties because this multi-process composite, in the multi-process composite, the void are randomly distributed in the matrix. Overall, when compared to a multi-process sample, 3D printed sample have a higher fiber orientation compared to load direction, as well as much many void, which act stress concentration point. However, in the 3D printed composite, the high degree of fiber orientation entirely overcomes the weakening effect of void. Despite the presence of void throughout the structure, the high degree of fiber orientation resulting in lighter and stronger materials. So overall, this result suggests that 3D printed composites have a relatively much many void than void process sample, but can compensate through strength of fiber orientation, resulting in the much lighter but stronger than conventional void process composite. In summary, our major finding of the presented study are as follows. We prepared a budgeted fiber reinforced periodic composite at different fiber loading and successfully fabricate a specimen using both FDM printing and mold process. FDM process produce samples not only with high fiber orientation, but also with high intervoid formation throughout the system composite compared with the conventional process. 3D printed samples have a relatively much many void than void process, but can compensate through strengthening of fiber orientation, result in much lighter but stronger than void process sample. The competition between the crucial factors such as fiber, length, orientation, and inner void determines physical performance of the composite. The future studies will more closely examine the variables in 3D printing to improve their quality and explore the resulting microstructure. If these efforts will continue to be made in the future, it will soon become possible to use a 3D printed composite for extensive range of industrial applications in terms of lightweight and strong materials. This is all of my prepared presentation. Thank you for your kindly attention.
Thank you. Thank you for the presentation, Dr. Siwan Yu. So now we can proceed further with the presentation of Dr. Xiaoyang Zhu from Qingdao University of Technology, China. Just a moment.
Okay.
Yeah. Now, Dr. Zhu, you can actually click on the screen and now you can just select the things what you want to share it on the screen. Or I'm sorry, do we have any questions for Dr. Siwon Yu? If any of you have any questions for Dr. Siwon Yu, please you can continue.
Mm.
Okay then. So I'm assuming there are no questions right away. So now, yeah, we can go on with Dr. Xiaoyang Zhu from
Okay.
Qingdao University of Technology, China.
Okay.
Hmm.
Bye. I finish my presentation. Thank you.
Thank you, Doctor. Yeah. Dr. Xiaoyang, you can actually select on the screen and you will have a pop-up where you can select applications. So it'll redirect you to the presentation, the PowerPoint presentation. Dr. Xiaoyang Zhu, were you able to connect? Are you facing any issues, Doctor? Is there anything I can do to help you out? Oh, I'm sorry for the inconvenience, Dr. Zhou Zhu has a net issue, internet connectivity issue. So, can we next move on with Dr. Muhammad Rabnawez from Michigan State University, USA? Yes. Yes, Dr. Muhammad, you can actually start your screen sharing right now. Yeah, your screen is visible, Doctor. You can actually start your presentation now. Uh, Dr. Muhammad, actually your screen is visible, but you're not, I think you're on mute. Could you please just check? Your voice is actually not audible to us. Uh, are you connected to any headphones or microphones like which has a mic? Yeah, you're connected to mic. I'm sorry, your voice is actually not audible, and I'm not sure.
Hello?
Yeah, now it's audible.
Can
Yeah,
you hear me now?
yeah, we can hear you. Yeah,
All right.
yeah,
Can you
yeah.
hear me now?
Yeah, we can hear you, Dr. Muhammad. You can continue
Hello?
with your talk.
Now?
Yeah, we can hear you.
Okay. Okay, good. So can I start now?
Yeah, sure, you can. You can start your presentation.
Okay, thank you.
Thank you.
Okay, very well. So my name is Mohammed and I am from Michigan State University, United States. I'm going to today talk about food safe chitosanzine dual layer coating for water and oil repellent paper substrates. This work has been partially sponsored by US EPA. Okay, so we are located in Michigan, right over there. You can see on the screen. We are located in the School of Packaging with undergraduate students, almost 800, and graduate students, 68. Here is my group. This is not the latest picture, but this is what I found for you guys. I think this is a year-old picture. We have several postdocs, multiple PhD students, and master students. Here you go. So we work on multiple areas, including the smart coatings, active coatings for a variety of applications. We work on the bio-based polymers as well, preparing materials and polymers from nature. We also work on the plastic recycling, chemical, mechanical recycling, because that is an emerging issue. But today I'm going to talk about something that we are heavily working in the area to develop plastic-free disposable cups, plates, and paper boards. So this is the area that I want to share with you today in this presentation. Do you know that how much paper boards is used in the packaging applications? So paper-based product by mass, 50%, 58% are used in the packaging. Okay, that's huge. And why is that? Because paper is really good, renewable, biodegradable, food safe, and good mechanical properties. But there is a problem when you use paper for packaging or other applications. This is the problem. You see, it absorbs liquid, oil, water right away, it absorbs. But in certain applications, you don't need to, they should absorb. Like if you're using this where you want like a coffee cup or something, you don't want this behavior, right? You want actually the opposite. So why we see this behavior, right? This behavior is due to the porous nature of the paper substrate. If you look in under the microscope, you will see paper is made of fiber, and fiber has those spaces, and they are perfect to provide the capillary action, absorption of water and other liquids. To address this problem, uh, commercially, 3 methods are used, right, to enhance the water and oil resistance of paper. One of them is called lamination. The other one is called coating, and the third one is called fluorinated chemicals treatment. All right, so what is lamination? Imagine you have an uncoated paper, and that paper, you apply a plastic film. We call that lamination, right? This plastic film can be low density polyethylene or PLA, polylactic acid, right? What is the challenge here? The challenge is when you use a laminated coffee cup, it's difficult to recycle because plastic separation from the paper is very, very challenging. So that's not a good idea anymore. You can also use wax coating on the paper or latex-based coating. Latex is something you have polymer particles dispersed in water. Both has their own limitations. For example, if you're using paraffin wax, number one, it is only suitable for low temperature applications. You cannot use a cup which is coated with the paraffin for holding coffee or hot liquids, right? Because it will melt it. And also, if you put a lot of paraffin wax there, their separation after use is challenging. The next one is the latex-based coating. The problem is when you have latex, you apply that on the paper, right? The thing is, this latex, when goes to the water streams, make one of the severe emerging issue. We call that microplastics. Microplastics are 5 millimeter or smaller particles. They are everywhere in the air, in the ocean, and what happens when and they become absorbent for the chemicals. So when suppose aquatic organisms like fish eat microplastic, they're also basically taking a lot of chemicals from the water, and those chemicals then when we eat fish, it comes to human beings. They become a severe issue. So what is the solution, right? Then people went into the PFAS. If you haven't heard about the PFAS, I will just use a very simple word, fluorochemicals. So people start looking into using fluorochemicals. And now if you look into this one, this is the percent of fluorine, percent with fluorine. So their analysis were done to see what kind of material that are used in the packaging has the fluorine. It was pointed out that most of them sandwich and burger wrappers, 38% has fluorinated chemical. Dessert and bread wrappers, they have 56% has a fluorine content. As a result, what is happening here in US and Europe, there is a big concern about the presence of fluorochemicals in different locations. And recently it has been, studies has found that PFAS fluorochemicals can reduce the immune response. So it can lower your immune strength, and that is also connected somehow to the COVID and virus diseases. So, you know, this is a big issue. So in very much in a nutshell, if you are following the conventional approaches to make uncoated paper, which is water oil absorbent, into water oil repellent, they ends up landfill, and from the landfill they just go to the, you know, they stay there, or they leaches out into the ocean. And in the ocean you will see that they are creating those problems. So as a result, many countries already ban the use of single-use plastic utility products in the packaging, right? Many companies, including Nestle and Starbucks and McDonald's, they promise that they are going to be 100% recyclable or 100% biodegradable by the end of XYZ years. Different companies, different particular milestones by year, right? Several lawsuits against fluorochemicals manufacturer. So there is a strong need for a plastic-free, fluorine-free paper-based coating, which has the properties of oil and water repellency. Okay, so we thought we can do something different. The idea was, if you have uncoated paper and then you coat this in a solution, a unique formulation, and let it dry, and this coating become water oil repellent. But the most amazing part, that when you do the repulping to recycle the pulp again to make paper, you can remove the coating. So the coating, which is the bad thing typically, should not end in ocean, should not end in the environment, right? That was the whole philosophy about this work. So we started our work with the single layer water and oil repellent coatings, right? If you look into this one, we started with silicone oil and chitosan. What we did, we grafted silicone oil onto chitosan, right? And then we apply that coating on paper substrates. Why we choose chitosan? Because chitosan has a strong interaction with the paper, so it will anchor silicone oil very, very firmly with the paper. That was the basic idea about this whole thing. Also, chitosan has a very strong grease resistance, right? Silicone oil, on the other hand, low toxicity, very low surface tension, and also biocompatibility they show, and good hydrophobicity. So we thought that silicone oil like this, grafted onto chitosan, and then apply a coating on the paper should give us both water and oil repellent properties. So we did coating on paper substrate, paperboard. Here is the paperboard example. You can really see that this paperboard or paper substrate, when we coated with the chitosan and siloxane silicone oil, it was not only water repellent, this is water, right? But also oil repellent as well. Okay, so that was really, really amazing to see that. And more importantly, it can be applied to other systems as well. Like, for example, you can easily apply this to wood or other porous substrates. And then the final step was, can we basically repulp? So these days, everything in the material science, they are talking about closed loop recycling, and that means zero waste, right? You start to reutilize those materials. So what we did, this is the coated paper that was water and oil repellent. We blended this and then washed this with 1% acetic acid to remove chitosan silicone oil copolymer, and then we iron that one to make, you know, and heat it to make recycled paper. What we found that if you do the washing treatment, the initial, you see this bottommost one, this is unwashed paper pulp. It has the peaks for silicone because we use Catterson silicone oil graft copolymer. But when we wash this with acetic acid, we were able to remove that completely. So that means that we can really do a good job using single layer Catterson and silicone oil system, and that worked very well. So after that, we went on to dual layer coating materials. We thought that possibly we can select, dual layer is having the first layer as hydrophilic material like polysaccharide, Catterson starch, and the second layer is proteins like zine, right? And the reason was zine has good water resistance, and the hydrophilic material like Catterson and starch has good grease resistance, okay? Right now, so this is basically the hypothesis about why we came with the dual layer approach. So imagine that if you have zine, which is hydrophobic, fully biodegradable material obtained as a byproduct from the bioethanol industry, if you apply that coating on paper, it has poor oil resistance. Oil just passes, but it can hold water. That means some sort of water repellent. And if you do the opposite, you just put a Catterson coating, right, on a paper, what will happen? You basically end up with something where the paper is more oil resistant because it's hydrophilic, but water readily passes through. So that's not good. So what happened, we thought that if you mix zine, which is hydrophobic, and Catterson, which is hydrophilic, you will end up with this kind of morphology. And that means you have oil resistance, Catterson slots, and you have water resistance zine coating. So what will happen, you will get a kind of moderate resistance to water and oil. But the most important thing of the whole hypothesis was if we are using oil resistance Catterson as the first layer and then apply water resistance zine as the top layer, so water will be held by the top layer, so water cannot pass, and then the oil resistance will be provided by the Catterson. So eventually, water stop here, oil stop here, nothing passes through. That was the idea. When we tried that, we were impressed with the performance that we got. Cob value, Cob 60 value 4.88 and kit rating 12. Now, what are these? Kit rating means that it shows oil resistance. 12 means maximum oil resistance. 0 means no oil resistance. Cob value is, so in our case, this Catterson zine dual layer, they showed 12 by 12 kit rating. That's amazing, right? Because that is the maximum. But if you look into the Cob value is something that when you bring, right, a certain amount of water against the coated paper, and how much water absorbed by that paper in 60 seconds. That's why it's called 60, Cob 60. How many grams of water being absorbed in 60 seconds by that paper per meter square. And if you look into this logic, the way I explained earlier, we were expecting that the dual layer where the zine is top, Catterson is the first layer, will really help. And we were very pleased to see that, right? So if you look into this one, the Cob value again is water resistance. The lower the value, the better. And you see if we have zine, 28% in water ethanol solution that was used, and Catterson 28%, this will give us really good Cob value. Oil resistance, if you look into this one, so Catterson, 12 because hydrophilic, so the oil does not penetrate, and so do our dual layer coating. So we really got very good oil resistance. The logic that why we are getting good oil and water resistance goes back to the same hypothesis that I presented earlier, that when you have uncoated paper, you have porous structure that absorbs water and oil, right? Now, when you add chitosan only, you fill the pores, right? That's good, you fill the pores, but it is hydrophilic, so it has a very high carb value, but good kit rating, sometimes 12. On the other hand, when you have zinc-coated paper, you again fill the pores, right? That's make it more hydrophobic, but hydrophobic not enough to repel oil. That's why oil penetrate there. But when you have a dual layer, you have smooth surface, no capillary action, and the surface is both water and oil repellent for a lot of uh, packaging applications. Then we tested the recyclability of coated paper as well. So I will start here from the E, this one. So we took as a reference, okay, as a reference, we took uncoated paper, pulped it, and remade the paper. So if you look into the color of this one, it's kind of, you know, bright brown kind of thing. And this is when this is our coated paper that we repulped the way I showed earlier and then recover the pulp. This is not good. You will see those dark things. This is zine. Because we just washed this with the DI water, deionized water. Then when we wash this with ethanol, it becomes much brighter because the zine is soluble in ethanol. But when we also add some acid, and again, it's not really good because acid does not help to remove the zine particles. So eventually, when we use acetic acid and ethanol that allow both layers. Now, acetic acid dissolve chitosan, ethanol dissolve zine. So when you wash with that combination, you get remove the coating from the paper pulp. Okay. So in summary, we have developed unique approaches for the water and oil resistant paper that is fully recyclable and fully biodegradable. We use silicone oil as well as zine coating as a replacement for fluorine and other thermoplastic like LDPE. This is perfectly a plastic-free approach, and that means we hopefully through these methods we will be able to eliminate the microplastic pollution. Carb value was 4.9 for the dual layer, and that's very, very impressive. That means you can hold coffee for several hours there without any problem. Pulp is recoverable. That's another exciting feature of this technology because uh, uh, the whole world in the plastic and the materials, they want to go into a closed loop and to reduce the pollution. So, okay, with that, thank you very much for your patience. I really appreciate your time. And if you have any question, you can just throw questions. Thank you.
Yeah, thank you. Thank you for your presentation, Dr. Mohammed. So, do we have any questions? Any of the delegates listening? Do you all have any questions? Okay, so I assume there are no questions. So, yeah, now we have Dr. Xiaoyang Zhu available right now. So, yeah,
Okay, I
thank
will just
thank you, Dr.
to
Mohammed, for your presentation. It was really
yeah,
informative.
sure. Thank you. Thank you very much. Yeah.
Thank you.
Okay.
Yeah, Dr. Zioyang Zuya, you can now connect the screen sharing. Yeah, your
Hello,
screen is
everyone.
visible right
Can you
now.
hear me?
Yeah, we can
Can
hear
you hear?
you.
Okay, thank you.
Thank you. Yeah, you can start your presentation now, Dr. Zioyang.
Okay,
Yeah,
thank you, Miss. Thank you. Thanks
thank you.
for your introduction. Ladies and gentlemen, I'm so honored to be here to communicate my academic ideas with you. The title of my academic presentation is High Performance Flexible Transparent Electrodes Fabricated by Electric Field-Driven Micro-Scale 3D Printing and Microtransfer Technology. I come from Shandong Engineering Research Center for Additive Manufacturing, Qingdao Engineering Research Center for 3D Printing, Qingdao University of Technology. The outline of this talk is listed as follows. Introduction to transparent conductive film. Fabrication of high-performance transparent conductive film with embedded zero mesh. Some related works and the conclusions. First of all, I want to give a simple introduction to the transparent conductive film, shorted as TCF. It is well known that TCF has been widely applied in many fields, such as touchscreen and displays, wearable electronics and electric skin, flexible electronic devices, and transparent electromagnetic shielding and transparent electric heating, and so forth. Because TCF is widely used in various fields, the performance of TCF needs to be improved to fulfill the needs of higher applications. So far, indium tin oxide, shorted as ITO, has been the most commonly used TCF, but there are still some bottleneck problems for the ITO, such as brittleness, scarcity of the indium, high heat resistance. All these disadvantages have limited its further applications in the TCF. As such, which material will be the next generation of TCF? In our personal opinion, the next generation TCF should have the properties of high conductivity, good transparency, excellent bending performance, strong adhesion and good surface roughness, low cost and large area fabrication. As we know, several emerging materials have been studied to replace ITO, mainly including conductive polymers, carbon-based materials, metal nanowires, metal meshes. As shown in the figure, we know that the metal mesh and the nanowires, may be the ideal materials of the TCF, as they have more optimal trade-off between the performance and the cost. However, there are still some disadvantages for the metal mesh and the nanowires. For example, the excessive surface roughness may be easily cause an electrical short circuit between the metal mesh and a top electrode. Based on these problems mentioned above, we proposed a simple and low-cost fabrication method of the high-performance TCF with embedded silver meshes. Firstly, the silver meshes are directly printed on the surface. Then the silver meshes are embedded into the flexible substrates. The whole process is very simple, including only micro-scale 3D printing and hot embossing, two core steps. It can achieve TCF with a good surface roughness, manufacturing with a low cost. The first core process is 3D printing the silver meshes on the substrates, while electric field-driven micro-scale 3D printing, which can be shorted as EFD micro-scale 3D printing technology. The EFD micro-scale 3D printing is a novel printing method where the electric field used is self-excited electrostatic field induced by a nozzle with a high potential, which is different from the traditional electrospinning. It has three working modes, which can take into account printing efficiency and printing accuracy. This is the paused contact mode and continuous contact mode, which can be used for fabricating micro droplets and micro lines. This is the forming process of contact and the printing process of the silver mesh. The second core process is hot embossing the silver mesh. The basic principle of roller-assisted embossing is that the negative pressure intake and the positive pressure intake setting on the side radial direction are converted sequentially. Combining the rotation of the roller and the horizontal movement of the substrate table, the flexible transparent substrates initially attached to the outer surface of the roller is gradually imprinted on the hot substrates coated with a silver mesh. Let's focus on the manufacturing results. The figures show the silver meshes before and after being embedded. As shown in the figures, we can see that the silver mesh can be changed from a rigid substrate to a flexible one and from a larger surface roughness to a smaller one through our process. Another advantage of our approach is that the silver meshes with a different aspect ratio can be printed on the different substrates by EFD micro-scale 3D printing. The manufacturing efficiency of silver mesh is particularly important for the industrial production. Direct printing embedded silver meshes with various patterns can be fabricated without additional process steps. As well known that photoelectric property is the most important property in tests of TCF. These two figures mainly show the embedded silver mesh photoelectric properties. The FOM figure of merit is calculated to be 1274. In our recent study, the FOM has been improved to be more than 30,000 through increasing the aspect ratio of embedded silver mesh. As we know that the adhesion between the silver mesh and the substrates and the stability of the silver mesh are especially important for the actual use of the TCF. The contact level between the silver mesh and the substrates reaches 5B using 3M Scotch tape. The bending results shows that the TCF has good bending performance. The mechanical stability of the TCF is also very vital for the actual use. The results showed that the change rate of the resistance of embedded silver mesh was less than 10%. You can look this picture. The change rate of the resistance was less than 8% when the silver mesh was in the ultrasonic environment. When the area of TCF is 60 millimeters per 70 millimeters, the FOM is 1237. We can see that the TCF has good heating performance. The temperature can reach to 70. All these test results show that the fabricated TCF has good performance. This part are some related work of ours. First is the fabrication of high-performance silver mesh for transparent glass heaters, where electric field-driven micro-scale 3D printing and UV-assisted microtransfer technology. The transparent glass heaters show the super photoelectric properties with a transmittance of 90 93.9%, a heat of less than 1%, and a sheet resistance of 0.2. The second is the stretchable electronics and paper-based electronics fabricated by EFD microscale 3D printing. The paper is slowly. The picture is slow. This picture. The second is the stretchable electronics and paper-based electronics fabricated by EFD microscale 3D printing. And the last part is the conclusions. This talk presents a low-cost fabrication method of high-performance TCF based on EFD microscale 3D printing technique and hot embossing. Differing from the traditional EHD jet printing with two-count electrodes, the EFD microscale 3D printing forms the electric field between the nozzle electrode and the top surface of the substrate, or printed structure only using a single potential by the nozzle electrode. The fabricated TCF shows a more optimal trade-off in photoelectric properties and surface roughness. It also exhibits stable bending performance, strong adhesion force, and good heating performance. Some typical applications, which include the transparent electrodes, transparent conductive heaters, stretchable electronics, paper-based electronics, are demonstrated. This property technique provides a high efficiency and low-cost TCF fabrication technique enabling high conductivity, good transparency, excellent bending performance, good adhesion, and surface roughness of TCF. This study was supported by the National Natural Science Foundation of China. I would like to thank all the members in my group. That's all. Thank you for your attention.
Okay, thank you. Thank you for your presentation. So does anyone have any questions for Dr. Xiaoyang Zhu? So if there are any questions, you can please continue. Okay, so I guess there are no questions. And thank you for your presentation, Dr. Xiaoyang Zhu. It was really
Thank you.
impressive. And as we are ahead of our schedule, so I would like to know, like, if anyone of you will be interested, like, as we know, Dr. Les Kalman, the next presenter, is not available right now. So I would like to know if Dr. Huang Yu Cheng, will you be able to present now, or we'll just go with a half an hour break for the lunch and then we can continue back? Dr. Huang-Yu Cheng, will you be able to present right now, or will continue with the break for half an hour and then we can go? Or if any of our participants in like the later session of lunch, if any one of you are ready, you can still continue with your presentations if anyone is volunteering, or we can just go with the break for half an hour and then we'll come back.
Hi, I wouldn't mind presenting already, if it's possible.
Oh
My
yeah,
name is Kristen. I'm scheduled for
yeah,
later
I got it.
this afternoon.
Yeah, I got it. Yeah, Dr. Christine Lusenberg. Yeah, you can please continue with the presentation then.
Okay, thank you.
Just a moment. Yeah. You can actually click on the share screen and you'll be able to see. Yeah, that's perfect.
Is it sharing? Yes.
Yeah,
Okay.
yeah.
Thank you so
Please
much.
continue with your talk, Dr. Kristen.
Thank you. So my name is Kirsten Lustenburg. I'm a researcher at TU Delft, and today I will be talking a little bit about my research, which is on non-assembly 3D printing for eye surgical instruments. So first, I would like to start by explaining a little bit more about eye surgery. So here we are looking at a cross-section of the eye, and there's two areas that are actually relevant for eye surgery, and that is the anterior section and the posterior section. So the anterior section is everything from the front of the eye up into including the lens, and a very well-known surgery in this area of the eye is the cataract surgery, in which the lens is replaced by an artificial lens. So everything behind the lens up to the back of the eye is called posterior eye surgery. And this is a bit lesser known as surgical procedures. But what often happens in posterior eye surgery is that a surgeon needs to have access to the retina, for instance, to fix a retinal detachment. So the retina is located all the way at the back of the eye. And in order for the surgeon to reach this area, he needs to go from the front of the eye all the way through the vitreous humor. And the vitreous humor is a gel-like substance that fills the globe of the eye and gives it its shape, among other things. But it's also attached to the internal structures in the eye. So in order for the surgeon to perform a safe operation, it is often necessary that he removes all the vitreous humor from the eye before performing the actual operation on the retina. So the removal of the vitreous is called a vitrectomy, and the instrument used in this operation is called a vitrectome, and it's shown on this slide. So the vitrectome consists of a thin hollow needle with a tiny cutter at the tip, as is enlarged here, and it has a cutting mechanism in the handle itself. So what happens during surgery is that the needle is inserted into the eye, and the cutter is able to take tiny bites out of the vitreous humor and aspirate it out of the eye. I have a small video that will illustrate this. This is from the perspective of the surgeon, so we're looking into the eye through the pupil. As you can see here, the orange background is the retina. We can see the needle of the vitrectome that is aspirating these tiny slivers of material, which is the vitreous that's being removed. So the vitrectome is quite an important instrument in posterior eye surgery, and this is why there's a number of patents that are on the market. A few are shown here, but what they all have in common is that they consist of a mechanism with a number of parts, which is very small scale. The assembly is also currently done by hand, which means that this is kind of an expensive step for this instrument since it's mostly disposable. So, and since it's disposable and the assembly step is quite expensive, the question arose, can we use 3D printing to create a working vitrectome in a single production step? So that brings me to non-assembly 3D printing. First, I would like to highlight the difference with a traditional way of manufacturing. So in the traditional assembly process, we'd first produce the parts by means of 3D printing or otherwise. You remove them from the printer, we clean them and assemble them into a working mechanism. For non-assembly 3D printing, however, what we want to do is 3D print the entire mechanism as a whole, after which it only needs to be removed and cleaned from the printer. This has several advantages. For instance, there's no assembly step, of course. There's also the option to add complexity to the mechanism due to the 3D printing process. There's no extra costs, and we can focus on the functional requirements only because we don't have to worry about any assembly requirements because the instrument is already assembled. So there's plenty of advantages here, but the problem is that there's very little information on how to design for non-assembly. And this is why I started by doing a literature review to see what examples of non-assembly mechanisms are already out there. And this literature research has resulted into a classification, which is based on the question, what really allows the prescribed motion within the mechanism? So this is the classification that resulted from this. I've defined 3 main branches that are based on the motion. So geometry-based, material-based, and pattern-based. In geometry-based mechanisms, the movement within the mechanism is foremost caused by the geometry and not so much by the material. While in material-based mechanisms, the material is responsible for the motion and geometry plays a lesser role. And finally, for pattern-based mechanisms, the internal structure within the mechanism in the form of a pattern will cause it to have motion. So I've defined also a number of subgroups, and I will go through these by means of some examples to illustrate what I'm really talking about. So the first group that I want to discuss is within the geometry-based mechanisms, which I've called multi-body mechanisms. And these really resemble the traditional way of manufacturing. So they consist of separate parts, although they are produced in a single production step. And an example is this prosthetic hand that's been developed within our group. And as you can see, the hand consists clearly of different parts, but it's able to be produced in one 3D printing step. Then within the same category, monobody mechanisms are actually mechanisms that consist out of only one body or one part. And this would include compliant mechanisms. So an example is shown here. And as you can see, by means of this very complex structure that is all completely attached to one another, so it's only one part. But by making use of these thin flexures, it's actually able to give this mechanism some kind of movement. For the next category, material-based, this means that the mechanism always makes use of some kind of flexible material to be able to move. In monomaterial mechanisms, this means that the only material that's being used is a flexible material. And an example of this are, for instance, prosthetic fingers. And there are a number of different hinges that have been tested that are shown on this slide. And what's interesting to note is that compared to the previous category, these hinges are much simpler of geometry. And that is because the flexible material is already causing enough motion without having to make a complex geometry. In multi-materials, the same trick is used, so flexible material. However, there are also different materials added, which are often rigid in nature. And this leads to some really innovative mechanisms that are very difficult to produce in any other way than by using 3D printing. And examples of this are, for instance, the mechanisms that are shown on this slide, which make use of pneumatic systems. So finally, for the category pattern-based, what I mean here is that the mechanism is built out of simple cells that all perform one small motion, but together, all combined, they make a more complex mechanism. And I have a small movie that will illustrate this a bit better. So this is a door hinge mechanism, but instead of consisting of several different parts, it consists out of one block of material. And by making smart use of very simple cells that all have one specific transformation, this the whole mechanism combined has a much more complex motion than each of the individual cells. So finally, now that I've defined these categories, my goal is to, or I found actually that it's important to have specific design characteristics and specific settings for printer in order to create a successful mechanism out of it. And I'm hoping that by combining these groups and understanding their requirements better, that it's possible to come up with design guidelines that can be used for the development and the design of non-assembly mechanisms. Thank you for your attention.
Yeah, thank you for your presentation, Dr. Kristen. It is really informative, and yeah. So, is there any
Thank you.
questions for Dr. Kristen? So if there are any questions, you may now ask her. So I guess no one has any
Okay.
questions. So yeah, thank you for your presentation. And yeah,
Thank you
it
very
was
much.
really good. So now we can go for a half an hour break and then we'll come back and we'll have the next 5 presentations. So as we know the time, so we'll all come back at 1:15 if you're all okay with this. So yeah, we can disperse now and we can come back at 1:15 for the rest presentations. Thank you.
Hello?
Yeah. Hi. Hi, Dr. Raskalman.
Hello?
So,
Yeah, I hear you.
yeah. So we are actually on a lunch break, so we'll just wait 2 more minutes so that everyone can join us back, if you don't mind. Will that be
No,
okay
no,
with you?
yeah, perfect. And where's all the controls here? Where's the share screen function?
Oh yeah, just a moment. I'll just make you the presenter so that you'll be able to. So yeah, now you will have a button of screen, so you can just select that and make your selection to share your screen.
Let's see. I gotta go into system preferences here.
Yeah, you'll have Chrome applications and every other, so you can just select whatever you want to choose.
Yeah. Okay, let's see if that works.
Mhm.
I gotta restart here.
Like, are you using it in your desktop or laptop? So,
Okay, so I'm restarted here. Still can't share the screen though.
yeah, now you can do it. Now, yeah. Now I've made you the presenter, so yeah, you can just select on the screen. Did you get that? Like, were you able
Yeah,
to do it?
it keeps sending me back to my security preferences. Just a minute.
Oh yeah,
Hang on one.
you'll have to change some security.
Okay, I'm on here. I got my mic, I got my camera,
One.
but I can't seem to turn the screen on or off.
Yeah, now
Here,
you'll be able to do it.
okay, let's see if I can get on there.
Yeah. So did you get that option?
Yeah, I'm just seeing which one I want to share with you guys. So I'll probably do this one. Let's see what happens if it comes up. So which screen
Yeah.
are you seeing?
Yeah, the title of your talk, application of titanium addictive. Yeah, that's the screen.
Okay, you just seeing one screen then?
Actually also having the next, to the right side, I have your Twitter and Instagram logo.
Yeah,
So
I
the
don't
next
want both
slide, that,
screens.
yeah.
I just want one screen. Let me do this.
You can
I
just
don't.
use slideshow here.
Yeah, but I have two screens on here. Hold on one sec. Let's
Yeah,
try that.
sure.
You still seeing two screens?
No, it's only the next slide screen that's displaying here. Other than that, no.
Oh my goodness. Let's do this.
I guess you can use slideshow over here, maybe.
Yeah, it should just be coming up one solid screen though. I don't know why your screen.
It's only one screen. Maybe it's because. Could you please try clicking on use slideshow? Maybe that'll
I
work
did
out.
already. Yeah, I did.
Oh, oh.
Okay. Well, let me turn this off for a sec.
Oh yeah, sure.
Figure this out.
Yeah.
Okay. Okay. Let's see what happens if that comes up.
Yeah, now it's only one screen.
Oh my goodness. Okay, this is gone. Sorry guys, I just keep getting so many pop-ups coming up here. So
That's okay, that's all right. So if it's working all right, then yeah.
well, yeah. Let's see.
Yeah,
Hey,
it's
what do
working.
you guys see? Is that working?
Perfect, only one second. Yeah, it's working.
Okay, tell me,
Yeah,
tell
so
me.
yeah, we can hear the sound.
Can we get everyone to mute their mics?
Yeah, I'm doing that. Just
And when you want me to start right now?
yeah, it's done. So everyone is on mute. So yeah, so we can continue with the talk right away. So yeah, here we have Dr. Les Calvin from Western University, Canada, to present us his topic. So yeah, Doctor, you can continue with your presentation.
Okay. Hello, everyone. Good morning, afternoon, evening, whatever time it is there. My apologies for the technical difficulties. I had two screens and they kept going in between one another. Anyway, thanks for lending me an ear while we get through this crazy time. I'm going to be talking to you about the application of additive manufacturing utilizing titanium for the production of a novel dental implant abutment. No, how come I can't go to the next one? That's not good. There we go. Everyone's still on?
It's perfect. It's perfect.
All right. If you need to get a hold of me, there's my email. ljcameron@icloud.com, and then on social media, I'm known as Doc Desmo, so you can reach out to me there. Okay. That's just a scan code. So throughout the presentation, there's going to be a few QR scan codes. So if you have your device handy, just load up the app, and then it's going to bring it to a few resources, our lab, and maybe some literature as well. So just a little bit about me. I'm an academic full-time, so I do teaching and I do research, and my research is in the medical device space. So we deal with medical devices, components, software applications, which led me to 3D printing with dental abutments. We've also been fortunate enough to release some software to industry. If you Google Maxalign, it used to be called Virtual Facebo. That was one of our successful research projects that we've been able to make available to the rest of our colleagues. I'm also a motorcycle enthusiast. I enjoy it a lot. This pandemic gave me some extra time, so I was able to put another book together. So this is Jorge Lorenzo, and he's hung up his riding boots. So I put together 99 images of number 99. And if there's any MotoGP fans out there, this is a QR scan code so that you can get a hold of that book. Okay, introduction, background, just a little bit of refresher for those. I work in this space of medical devices, and when we think about a medical device, what you should be thinking about is something to restore, correct, or modify the body structure, okay? And we're looking at improving function, aesthetics, and dental prosthesis fits right in there, especially with dental implant abutments. Additive manufacturing, pretty well synonymous with 3D printing. We start seeing a huge footprint in dentistry, mostly with resins and plastics. We start dabbling now with metal. That's basically my space, as well as aesthetic materials like ceramics. So that's something that we're going to be moving on. If you're in the implant space and you order components, most likely they're milled. Okay, so we're still dealing with milled dental implant components. And it would be interesting to see if we can open up the additive manufacturing branch of dental implant component manufacturing. So for those that aren't familiar with dental implants, this is what an abutment is. You have the dental implant that fits within bone. You have the tooth that would go on top, and the implant is the interface between the two. It could be one piece, it could be two pieces. So again, what we're exploring is, can we make that dental implant abutment in a non-traditional fashion? Can we make it through additive manufacturing? That's what we're talking about. So I don't know if the video will be working. I need some sort of confirmation. I'm going to start it now. Hopefully it works and you hear what's happening. This gives you a little bit of background as to the novel dental implant that we've developed.
It's working. The video is working.
So I hope everyone had it. I hope it wasn't too laggy and the frames per second work. But when you see the implant abutment that we developed, that will hopefully contextualize why we made the design, so that you get an idea about the process for temporization. The research that we did, we were fortunate enough to feature in 3D printing and additive manufacturing. And there's a copy of the article, and I'll have a QR scan code at the end of the talk if anyone's interested. So let's get right into it. So the methods and materials, the dental implant abutment that we have created, there's been some extensive work to get to where we are, so it has been patented, okay? And what we've done is we've played around with this product before, but we try to manufacture it conventionally, and that would be basically taking part A, part B, part C, and trying to put it together, usually through laser welding if we were fortunate enough to find someone. And that kind of medical device is what we would test, but it wasn't working out. So we have to look at a new approach. So what we did is we created a digital model of the implant abutment, and we refined that optimally. And this was all done at a place called the DS, which is here in London, Ontario, and they're an additive manufacturing facility that works with metal. And once we've refined that, we then went ahead and printed it. Okay, and we printed it with TI64. And that was printed with the Renishaw AM400. There'll be a picture of that coming up. And the approach that we used was using SLM, otherwise known as selective laser melting. So the idea here is we've taken a device that we played with and we fabricated conventionally. We went ahead and digitized it, refined it, and then printed it. And that would be the kind of workflow of Methods and Materials 1. That's what we're talking about when we're talking about the Renishaw AM400 printer. So this is not a desktop printer. This is very large. This is probably about 7 feet tall, 3 feet in, and 5 feet across. And you know, budget for something like this, you're probably looking around 750,000 Canadian dollars. So you know, in terms of dentistry, not a lot of individuals are going to have this, and they should. This is an industrial grade. So once we started printing, we started realizing that we have to optimize particular items on the implant abutment. From the animation, you saw that we have these little pin projections that come off the abutment. We have a diameter that goes into the implant. So we had to figure out the optimal geometric shape for that. So that took a bit of time, okay? So here's an image of a conventionally manufactured one where we took an abutment and we welded on some pins, and that's kind of what we have. This was the sample set that we had when we were working, and you can see the enormous variability, okay? Pins all over the place, different angulations, some were useful, some were not, some were already damaged before we got to it. This would be an additively manufactured prototype for the shaft. So you can see the base is still a square. We haven't gone ahead and printed the head of the abutment yet. And what we're trying to do is optimize that shaft that's going to thread into the dental implant. So material and methods 2. Once we figured out A, B, C, and D and the right dimensions, post-processing is mandatory. And when we're talking about post-processing, it's after it's printed, what do we do to it? So bead blasting, which is essentially sandblasting. The second point, which is fixing them into a custom stabilization jig. I will go through that in detail so it makes some sense. And then we have to assess what we're doing. So we have to thread them into a dental implant analog, make sure the threading feels right. It can't be too loose, it can't be too tight. And then we also check radiographically with the dental implant abutment. So for those of you that haven't seen additively manufactured products before, this is what the build plate looks like. So once the dust is wiped off, this is your raw kind of device. So as you can see, there's a little frosting on there. That's not a filter or anything like that. They literally come out like that. So I think you can appreciate that this isn't like baking cookies in the oven where when they come out, they're ready, you know, we're ready to eat them. There's a lot of post-processing that needs to be done with the components. This is the custom stabilization jig that I was mentioning. So this had to be designed. And what this is basically an anchor or receptacle for the dental implant abutment so that it fits in. You can see those pin projections will seat right in, and it's meant to hold our implant abutment so that we can actually put threads onto the shaft. So on the left-hand side, you can see the implant abutment is put into it. On the right-hand side, it's within a vise. And now the shaft is ready to thread. On the left-hand side, you have a standard die, and on the right-hand side, you can see that it's a manual process of introducing threads into the shaft. These would be the threads that engage the internal component part of your implant abutment. So if we do a comparison, if you look on the left-hand side, this is your finished product, additively manufactured implant abutment. And on the right-hand side would be the conventionally manufactured abutment, which is ones that were laser welded together. And then there's just a close-up. So the 3 receptacles, that's going to retain your temporary restoration. The driver fits in the center, obviously, and then your implant body will screw right into the threads. So on the left-hand side, we have a Straumann tissue level implant analog where we're threading and checking the play. And on the right-hand side, we have the radiograph of the same just to assess the seating. So that's the workflow. So that was the bulk of this research, is how do we get from the start into the finish? How can we create a finished product that we feel would be sufficient to act as a temporary abutment for dental implants? And that's our flow chart. We went a little further. We went ahead and did some testing. So for us, the strength of the pins was very important. So this was an Instron machine. This is pretty standard. The abutment was placed in the implant. The implant was placed in a custom resin jig and the metal housing. And essentially, we put a progressive load until the pins fail or break. We also wanted to check the tightening. Can we thread this into a dental implant? If anyone's worked with implants and abutments, when you have something fracture off and the screw is retained inside the dental implant, it's an unwanted outcome. So we wanted to make sure that the abutment could withstand the threading necessary. So this was the pin strength chart. So the black is additively manufactured, and the gray is conventionally manufactured or laser welded. And I think you can appreciate that the additively manufactured pin strength is much higher. And that's something that we would expect, okay? Based on previous studies and the SLM process, it's quite high. Well, then let's talk about torque. Where are we? So before we look at the 2 boxes, just look at the shaded area. It says recommended torque of temporary abutments. So we have to appreciate that what we're talking about is a temporary abutment. So a short amount of time that's not torqued down too high, and we're talking anywhere from about 15 to 35. So again, the black would be the additively manufactured, and the right would be conventional, and there's our variabilities. The AM was lower than the CM, and the reason why, where the receptacle fit with the wrench, we had slippage. So we actually had a geometric flaw in the design of our abutment. So even though this is data, it's not true accurate data, and we'll have to go back and revisit this. So the results, the first and foremost, is that additive manufacturing in titanium can provide us with a component that we can use. That's the most important part. And we can kind of check off that box and say that this works satisfactorily based on subjective assessment, okay? Seeing how it fits, feeling how it fits, and checking out radiographically. The data seems to suggest that we have pin strength suitable enough for provisionalization or temporalization, and we also have torque that could withstand what a temporary abutment needs to withstand. So again, please bear in mind this was a preliminary investigation with a fixed budget and fixed time, okay? But we were able to develop the workflow, and we were able to publish the workflow, and we will use that to move forward in our next steps. A couple of highlights when you're working with AM versus conventional. So when you play with additive manufacturing, you have this amazing opportunity for customization. Okay, we already went through how the iterations of the abutment have to change. Maybe the pin length has to be longer. Maybe the shaft diameter has to be increased. This is very, very easy to do digitally, and then we just translate it to the production end. So it's quite simple. High consistency. The nice part here is that pretty well every single abutment we were able to use, and that was unlike what it was like outsourcing to have something conventionally manufactured. Here we had a tough time finding something that was suitable for testing based on the difficulty of laser welding. Cost of production was extremely low. For us, it worked out to about $9 Canadian per abutment, which is very low. Just to give you an idea of the traditionally manufactured laser welded one, we're talking about $225 cost for the production of one. So a couple of orders of magnitude lower. Fabrication time, this is quick. Okay, you hop on the computer, you do your digital design, you send it to the printer, and away you go. The converse of that is sending out something to a lab. finding a lab that's comfortable doing it, and then waiting for it to come back. So there's a lot of convenience with time. The challenges, well, the first one I'll read off is number 2, and that's post-processing. Trying to get the threads on that tiny, tiny shaft is very, very challenging. I had a very, very difficult time, and a colleague of mine is the one that did all of them. So a real challenge. It would be nice to see if we could actually print the threads on newer productions. And then the subjectivity. So I think we're all aware that additive manufacturing, it needs to have some standardization. Well, that needs to come in our play as well, because there's a very subjective and biased determination of what works and what doesn't. So conclusions, first of all, it's a lot of fun and it's a very interesting avenue. And I think that additive manufacturing in metal will have a place for dental implant components. If you've been following the news, additive manufacturing is being used for many things with metal. If you're familiar with the car manufacturer Bugatti, they make their brake calipers through additive manufacturing. Porsche does their pistons. So on an industrial level, we know that medicine is really utilizing it for simulation. And I think this space will slowly start moving from milling into additive manufacturing for dental implants, okay? It's efficient, it's cost effective, and the customization is something that can't be overlooked. Like any study, as I mentioned, this was preliminary. This gave us some fun data, gave us some good insights, but more money would be required, more samples would be needed, and would need to expand this research so that we can really optimize and get some solid data. We couldn't have done this without the support of all our partners. So first and foremost, the ICOI. And if you're unaware of that, that's the International Congress of Oral Implantologists. We were kind enough to get an IDREF grant to support our work. This was also supplemented by my employers, Schulich Medicine and Dentistry, who were kind enough to help us out. Research Driven is a company that also gave us some support, and then Adias, there were our industry partners that helped make the component. References, if anyone's interested, are there. You can email me, DM me, whatever we do socially, and I can get you those if you'd like to know what's going on. So the publication for the additive manufacture development, this would be the workflow development is there. So if you have 10 seconds and you have your app open, just give that a scan and it'll take you right to there. This is a scan code for our lab. Just bring you to it. We're involved in some pretty exciting stuff. So if you're interested in seeing what's there, if you're open to collaborations, please give that a scan. That will bring you to us, and well, we can go from there. Okay. And then last but not least, yeah, I have 2 boys. One's 18, one's 13, and my 13-year-old told me that I should include a little bit of a little whatever that is, GIF, so that we can end our talk. Okay, let's see if I can exit out of here. And if we have any questions, we can take them. Bear with me.
Oh, yeah. So that was really informative. Thank you for your presentation, Doctor. So, yeah, is there any questions for Dr. Les Calvin? So is there anyone who's having any questions? So yeah, I guess there are no questions. So yeah, thank you for your presentation, Dr. Les Calvin. So,
all right, sorry about the technical details. Yeah, if anyone has any questions, please reach out through email. And thanks for everyone's time.
thank you for your presentation. So yeah, now moving on to the next one. So yeah, we have Dr. Huang Yu Chen from Penn State University for our next presentation. So, Dr. Huang Yu Chen, you can just click on the screen below the options, so you'll be able to.
Okay, sure. Let me take a look.
Yeah.
I think the system asked me to restart. I'm not sure whether there's a problem.
I know maybe it's because of the security system. So you can just restart. Yeah.
Mm-hmm.
You can just log out and log in, so it'll be available.
Okay, so I think I'm back here, and you just asked me to do that again, so I'm not sure what is going on here. Okay, it's working now, and I think I can share the screen. Are you able to see my screen? Is it working? I think it's working, so I will just get started. Good afternoon, everyone. My name is Larry Chung. I'm an assistant professor at Penn State University. What we have been working on centered around the wearable devices and is to detect the vital signs and the relevant parameters for the healthcare. And today I'm just going to present something relevant to COVID-19 as well, since the challenging time is relevant and interesting to some of the people. And before I get started to talk about all the details, just want to mention some background in terms of technology we have been working on. So getting back to the wearable devices is not something completely new in the past few years, but rather old topic for at least a couple of decades. And this is from early imagination where people start to imagine or think about this technology back in 1930s. It was regarded as a surrealist painting, but is not possible until we have the right tools to make it reality. And here, we just want to point out one single aspect is to prepare the devices or system into actual thin geometry. And it is possible for us to do this through a lot of different fabrication approaches. And 3D printing, additive manufacturing is just one of the easy tool we can use to design this system and fabricate that into a thin geometry. And the reason behind this is the flexibility of the material, or the capability to flex is related to the thickness or bending stiffness. And the capability is directly proportional to the thickness to the power of 3. So if we reduce the thickness to 1/10, the material will just become 1,000 times more flexible and easier to bend over a certain radius of curvature. So that's why we would like to go for the thin geometry. But still, if we do this, is flexible but not stretchable. And the stretchable property is important when we have to deploy this onto the complex 3D surface like the elbow, finger joint, or heart, or this type of different 3D surfaces. And the flat surface can only be applied on, for example, a corn cylinder or this type of so-called developable surface, but for the other complex surface, it's not possible. And people realize is nice trick to play with if we have the stretchable property, because if we just unfold the 3D globe into a 2D map, and we just have to stretch the north and south pole of the globe so that we can do the mapping. And this is true for the wearable devices as well. If we would like to deploy the planar geometry for the sensors onto the target 3D surface of the heart or the other complex geometries, we will just have to stretch them. And in terms of design, we have a simple technique, which is to have these devices break into smaller pieces, and then they are interconnected through the wavy geometry, pretty much like the spring we used to play in the daily life. And if we think about this, it's really something trivial, but it can actually enable the structural property for the entire system. And think about the straight wire is not going to be stretchable if we have a single wire in a straight geometry. But if we design into a serpentine geometry, we'll just be able to stretch them into a larger area. And that's really the idea behind this actual stretchable battery. When we stretch the battery, the islands will just be bonded to the underlying substrate, but the interconnects in between the islands, the blue islands, will just unfold and follow deformation applied to the system. So that's how we stretch and enable the large deformation to the system. And of course, building on this platform, we would like to further enable the comfortable property to make sure the device on the skin is comfortable wear and also soft and possibly mechanically invisible, so that we don't even feel there's something out there. So we'll just be imperceptible and much be preferred by the users. And here behind this, we have designed a new technique to separate the function into two different layers, and the top layer will just be able to stretch, and the bottom layer will just be a magic layer, so that we can design that to be high strength to prevent the possible damage to the system. And how that is done, we're just going to show that in the next slides, but just want to show one video to illustrate the possible application in the human-machine interface. And this is done through a device on the forearm. And if we capture the electrode signal from the forearm in terms of the EMG, and the muscle movement will be captured and classified into commands to control the drone to wirelessly fly within the room. So we can easily control that to take off, fly forward, make a rotation, and come back and land on the ground. So it's quite a simple demonstration. And next, I'm going to show you how we can do that high strength development and further to provide this mechanically invisible design. And this is done through a bio-inspired strategy. When we look at the skin on different locations of the human body, we'll be able to find out they all have this wavy geometry. So if we zoom in, we'll see different wavy serpentine-like geometry in terms of the elastin fiber we have inside the tissue, and that will just allow us to do this magic we just mentioned. And why is that the case? If we stretch that along, say, horizontal direction, we will be able to first rotate the wavy serpentine and align them along the stretching direction. And if you further stretch the material, it will just become much stiffer because you are stretching each individual fiber. So if we plot the stress strain curve, it's going to be highly nonlinear, and it's not a linear curve, and it's pretty much like a J shape. And the slope will indicate the modulars of the material structure. So initially it's very soft, and when we stretch that further, it becomes stiffer and stiffer until a point they become much larger than the initial value, and they just provide a higher strength for the entire system, so that for a larger force you apply to the system, it won't break the system. So that's really something evident from the skin. So if we play with the skin, say if you stretch your forearm on the left hand side with your right hand, you'll be able to stretch that easily by about like 10%. But if you keep stretching, you won't be able to stretch that further, even if you increase the force by 2 times, 3 times, or even 10 times. And that's really one kind of self-protection. And also something we can learn from our system, so that we mimic what is in the wavy geometry, but design that into an engineered fabric, so that is stretchable, but well controlled, where we have few parameters we can play with, but without randomness in the biological system. So we can decide the effect from each parameter, and our system will be able to reproduce this highly nonlinear property. So as you can see here, we have two of these curves, and the blue line is from the incremental measurement of the skin tissue, and the dotted line is from our design, and they pretty much match with each other, indicating our design will also provide the self-protection from the device, but also to reproduce pretty much everything in the tissue, and it gets become mechanically invisible when we place this on the skin surface. And if we simply replace all of the previous sensors, say the battery with LEDs and a few others, we'll be able to design the ultra stretchable LED and strain and hydration sensor to capture the possible deformation, respiration, and the skin hydration level through a wireless measurement. And we can also do that for temperature sensor to capture early infection, say from COVID-19 and a few other different disease applications. And we can also reverse the signal from measurement to stimulation. If we drive in the current, we'll just be able to provide this electrical stimulation to provide a sensation, massage, or wound healing process. So that's really something important and desirable for the actual application. And the wireless communication can also be enabled through near field communication of the data or energy, so that we don't need to rely on the wires. And next, I'm going to show one recent development in our group to highlight how that process and design consideration can be leveraged to enable new type of sensors. And this is the gas sensor we're going to talk about, and is completely fabricated through a simple laser process. And the laser is simply available in the machine shop, and it's a CO2 laser commonly available and easy to scale up. Before I get started with the detail, just want to mention a few backgrounds information about the gas sensor, because it is widely available in the human body in terms of volatile compound, so that we are interested in capturing the information from the human skin, so that we can help inform the health condition, and for example, lung disease or pulmonary fibrosis, and that's quite important. And in addition to the healthcare, we are also interested in the industrial safety and the environmental exposure of the toxic gases. So that's why we got interested in the wearable gas sensors. And for wearable gas sensors is less studied in the past, as opposed to the physical parameters we have been measuring in the past. And there are a couple of challenges we have to face. For example, the first one is most of the nanomaterial will have to operate at a high temperature from 100 degrees C up to a few hundred. So that's not really something compatible with a human body. And also, the nanomaterial is really effective because of the high surface to volume ratio. However, they are not easy to hook up to the wiring system or the data acquisition system we have, because you cannot really connect a single nanoparticle to the wires. So what people have been using is the so-called interdigited electrode. So there are electrodes with two fingers or multiple fingers in between them, and the nanomaterial will simply be drop cast onto the interdigited electrodes to bridge the electrode to provide a conductive pathway. So in this sense, it's not really simple and straightforward to fabricate the electrode with a spacing on the order of nanometer. Otherwise, it would just be very expensive. So here, we just want to address those two challenging issues by going through this laser fabrication approach. So what we have done is we use the CO2 laser, but it could also be UV laser, femtosecond laser, and they just go through the pattern as designed and then convert the polyimide material into a highly porous graphene. And the material is 3D in geometry and also be able to directly compatible with the nanomaterial. And the other to localize the heating, we also coat the other serpentine region with the silver, so that the resistance in the middle region is about 1,000 times larger over the other areas. So when we apply the nanomaterial in the center region, and the temperature will just be highly localized in this region to heat up the material. And this is simply because the Joule heating that relies on the resistance difference. So if we're driving a small current, you'll just be able to heat up the material at the largest resistance, which is in the center region. And we can disperse different materials, or in a different route, we can disperse the nanomaterial precursor before the laser scribing process. And then when you do the laser scribing, you can directly integrate the nanomaterial into the platform without separately dispersing the material afterwards. So it's just so versatile to be compatible with a lot of nanomaterials. And because of this 3D geometry, it becomes ultra sensitive to the low concentration of the nitrogen dioxide. So here we have demonstrated detection of 10 ppb, and it's about like 10 to the power of -6, and it's much better than the available materials from the literature, which is typically on the order of 100 or even more. And we want to capture the ultra small fluctuation in the environment or from human body to inform health condition. And the other property is the stretching capability. Because of the serpentine, it can withstand the large deformation, so that it can be stretched over 20% on the skin surface. And here's one demonstration. We simply apply that on the skin surface. You can see how that is going through the deformation without breaking. And more importantly, every material is sensitive, but there's no absolutely selective material. So when we think about one example in the home, that's really the smoke detector we probably are familiar with. If you don't close the door when you take the shower, it will just go off when the moisture built up in the room. So it's just one example on how not selective the material is. And there's definitely not a great strategy at this moment, but our strategy is relatively compatible with large-scale fabrication, because everything can be fabricated in a rapid manner and also high resolution. So we can definitely do a large density array with different nanomaterial, each to be specific to the target gases, and then put them together in an array. We'll be able to deconvolute multiple gas species from the mixture. So that will just be one route moving forward in the future. And this can also be applied to antenna and wireless communication. And I guess I not have much time, so I'll just try to skip the detail, but just show you and show you the quick idea about what can be done. So, any questions?
Yeah, so I just need to check. So, do we have any questions for Dr. Wang? Sorry. Do we have any questions? So I guess there are no questions right now. So yeah.
Okay, I'll just continue.
Yeah. So now, yeah, we can. Thank you. Thank you for your presentation. It was really informative. So yeah, thank you.
You know, I
So
probably
now
reaching
we'll
to the end of
continue
my
with our next.
presentation. I'll just continue with 1 or 2 slides and wrap up at that moment. And I'll skip these slides, but to show the last one in terms of the biodegradable devices that can be dissolved inside the human body or the environment. And the idea is to realize the system with biodegradable material. So that will be all possible, and the material can be ultra thin. So the amount of material in the device can be even smaller than the daily intake. So everything will be safe without worry of the possible biohazard. And I'll skip this one. And to show how this is dissolved when we dip that in water, you will see the process in the first few minutes. But when we put this together into a complicated system, we'll be able to capture the important information from inside the human body, say the sleep study or the cranial space for the temperature and pressure measurement. And lastly is one demonstration for the COVID-19 infection. We have recently fabricated a new material that can be directly inked onto the skin surface to capture the parameter relevant to COVID-19. And this is demonstrated through two relevant parameters. One is the heart rate to capture not only the heart rate, but also the ECG to inform the cardiac function. And the other is a trend in blood oxygen saturation to inform the lungs function. And both of those compare favorably with the commercial devices. So that will help us to get all the information to indicate how the COVID-19 patient will go through the severity level from mild into severe condition, so that they will be able to get to the hospital before it's too late. And I know that's probably I have in terms of time, so I'll just stop here and to see if you have any questions. Any questions?
So yeah, do we have any questions now? No, I think so. There are no questions now. So yeah, we'll be sharing you all the email IDs of the presenters. So if you're having any personal questions, you can really ask them through email, or yeah, we'll definitely do that.
Okay,
So
that sounds perfect.
Thank you for your presentation. And I'm really sorry for the
Thank you.
interruption before the mic just got on. I'm really sorry for that.
No problem.
Thank you. So yeah, now we'll just move on with our next presentation. Yeah, next presentation with Dr. Eduard Zakanwich from National Technical University of Belarus. And yeah, doctor, you can just select the screen, the option present over here in the bottom. Yeah, perfect. Uh, yes. Your voice is actually not audible. Could you please on your unmute just the first option in the bottom? Uh, are you using any mic or headset? It'll be easy for us to hear you. We're not able to hear you. I'm sorry, Dr. Edward, could you please use a mic or headset? If you can use your mic or headset, it'll be audible, and please unmute in the place of mic. the screen is perfect. The screen is perfect, but in the meetings place, you can just click on mic at the bottom.
Are you? It's okay, Mike.
Yeah. Now we can hear you.
So, do you hear me?
Yeah, we can hear you now. So you can change your
So people
screen.
can screen now. I see people can see your screens. That's why may I install my presentation and people will see it. Yeah. Okay.
Yeah.
Now I will try. Yeah. Okay.
Yeah, it's perfect.
Yeah. Okay. So this is okay. So in fact, I installed my PowerPoint presentation. So and may I start?
Yeah, sure. You can start your presentation.
Just immediately. Yeah. Sure.
Yeah.
It's fine. It's fine. Okay. So. My talk may be maybe connected not with let's say with implementation of some nano devices, but maybe connected with basic ideas what may be used upon preparation of some nano devices. So my talk is self-assembled nano composites based on semiconductor quantum dots and porphyrin molecules. So I would like to discuss interface chemistry, optical properties, and relaxation processes in quantum dots being attached to functionalized porphyrin molecules. Now, how to? Okay, so it is not now. It's not understandable. Now it's understandable that nanomaterials plays a significant role in our life. And I should say that it's only maybe first steps to use nanomaterials in real practice. But you know, I guess the audience knows that nanomaterials may be used in various applications like electronics, optoelectronics, biomedicine, consumer products, and so on and so forth. So if one deals with semiconductor nanocrystals, we should take into account that the size of quantum dots or semiconductor nanocrystals plays a significant role in the optical properties of these compounds. It means that when we change the radius of quantum dot, we change the size of quantum dots, we may shift the absorption bands and the photoluminescence bands to the red or to the blue, depending on the size. So it's a so-called quantum size effect, and this very useful property, which is used for using of nanoparticles in different scientific investigations. When the size becomes smaller, the energy gap between conduction and valence becomes larger. It means that we have shift of properties to the blue. Absorption band of first excitonic position shifts to the blue. That's why we may use different kinds of quantum dots in order to tune their optical properties for necessary needs. In our investigation, we used two types of quantum dots: cadmium selenide quantum dots and water-soluble quantum dots, which based on silver indium serum quantum dots is a composition covered by zinc S layer. So typically, people silent imagines that quantum dots may be considered like data de Leon. The properties of quantum dots seems to be very similar from different kinds of quantum dots. It may be, in this case, we may consider quantum dots like ball with the homogeneous distribution of its properties. But it is not the case, and I will show you that in some cases it is a very simple presentation of quantum dots, and we should take into account some structural properties of these compounds. So in order to, if we are going to prepare some nano devices, we should take into account that we should combine organic and inorganic compounds. And the main problem on the path to develop efficient nanomaterials is our limited understanding of quantum dot surface interaction with surfacely attached molecules, and how these molecules may impact on quantum dot excited states, including charge or energy transfer or formation of new states. So it means that in our case, we used porphyrin molecules like a specific functionalized probes in order to test the quantum dot surface, morphology, optical properties, and energy states. Typically, when we have quantum dot, from the first point of view, it is not a ball. It is not a homogeneous ball. Typically, it seems to be presented like a rock with some different facets of different properties. One thing, and second, when we prepare a quantum dot with functionalized molecules, so we should take into account some specific phenomena which should be taken into account in order to explain the properties of quantum dots or the properties of nanoassembly based on quantum dots and molecules, and in order to prepare some functional devices. So it means that when we prepare quantum dot dye nanocomposites, we should take into account the influence of solvent. Then we should take into account the dye distribution of molecules on quantum dot surface, and in order to analyze all these photophysical processes, we should use temperature experiments in order to test exciton-phonon coupling in such systems. From the experimental point of view, it's necessary to use not only steady state spectroscopy, but we used the laser kinetic spectroscopy in order to measure photoluminescence kinetics, and we used the palm probe experiments with picosecond time resolution in order to test the intermediate short-living excited states. And in addition, we used the single nano object detection in order to see what happens on the one nano object level in this case. Let me start with the first part of my talk, which connected with the probing of quantum carboxylene quantum dots properties by attachment of pyridyl substituted porphyrin molecules. So typically, when we attach porphyrin molecule to quantum dots by the so-called interactions of nitrogens with zinc atoms of surface. In this case, what we may observe, we observe that in absorption, upon titration, we observe that the increase of porphyrin bands in the spectrum, and in addition, we observe the strong photoluminescence quenching of quantum dots. The intensity becomes smaller, and we observe the photoluminescence decay shortening in this case. It means that upon interaction of quantum dots with porphyrin molecules, we have the quenching of excited states. The problem is, what is the reason of this quenching? And it is interesting to note that in this case, we may observe the same quenching when we used single quantum dot with attached porphyrin molecules. So on the level of quantum dot detection, we also observe that we have the quenching of excited states, presumably at one nanocomposites. The question is how to say it? The question is an example of formation of our nanoassemblies, but the problem is, what is the real mechanism of such quenching of photoluminescence of excited states of quantum dot? There, it's possible to take into account few possible mechanisms: energy transfer from quantum dot to dye, then charge transfer, electron or hole transfer in these systems, and some perturbation effects and formation of trap states upon attachment of quantum dot to the surface of attachment of porphyrin molecules on the surface of quantum dot. So we tested all these possibilities. First of all, we used different porphyrins, but with the same fixation manner, and found that when we change the redox properties of our porphyrins, we did not observe the changing of quenching effect. It means that from these experiments, we did the first conclusion that photo-induced charge separation with participation of porphyrin molecular orbitals does not play the essential role in the quenching of our quantum dots. Second, a typical maybe upon interaction of quantum dot with porphyrin molecule, we may realize the energy transfer. Okay, we tested the situation, and transfer should take place from quantum dot to porphyrin moiety. But detailed experimental analysis has shown us that the efficiency of energy transfer, this is red curve, the efficiency of energy transfer is only 10% with respect to the total quenching. So it means the total quenching is very strong, but the energy transfer, the percentage of energy transfer is only 10%. It means that the main quenching process, it is not connected with energy transfer. Energy transfer takes place, but it is not the only one channel of the activation of states of quantum dots. So we calculated such systems using the corresponding density function theory. And if we take into account only one process, I mean energy transfer, so energy transfer should take place according to calculations within the time of 30 nanoseconds. But in reality, the quenching realized is the time within few nanoseconds. It means again that the quenching process via the quenching processes via energy transfer is not only one reason of the quenching in our case. So after that, we pay a serious attention on the quantum size effect. It means that we used the same one porphyrin with one type of fixation on quantum dots, but we changed the size of quantum dots. So we changed from the diameter of quantum dots was from 1.1 nanometer up to 5.2. So and we titrated our system with the same porphyrin, and we observed that the quenching is stronger for smaller quantum dots, these blue points. And if the quantum dots, if the diameter of quantum dots increases, the quenching process becomes smaller. So this effect, as we explained, this effect is connected with the so-called quantum size effect. What does it mean? It means that when we have excited exciton in quantum dot, it means that electronic wave function may spread over the barrier of zinc S. The electronic wave function may be spread over the boundary of quantum dots. It means that the excited electron hole pair may be spread over the boundary. After that, we used the theoretical approach. We calculated using the quantum mechanics. We calculated the squared value of wave function and compared with the corresponding rate constants. So we received the good coincidence between psi squared and rate constant. It means that in this case we have the tunneling of electron through the zinc S barrier in the conditions of quantum confinement. It means that upon attachment of porphyrin molecules to quantum dots, the main quenching process is connected with capturing of this electron on the quantum dot surface. It means that the next step is to analyze what happens on the quantum dot surface. So in this case, it's necessary to take into account some possibilities. First of all, for the induced self-trapping of charges in the electric medium, maybe the dynamically controlled attachment-detachment process, and the formation of quantum dot surface states, which may play the role of traps of electrons, of excited electrons, of exciton pairs. So it means that in this case, the next step is to find such specific trap states in our quantum dots. So typically, from a basic theory, from the basic quantum theory of quantum dots, such trap states are not taken into account. It means that for pure quantum dots from quantum mechanical situation, we have the pure excitonic states in the conduction band and the corresponding levels in valence band. But when we take it into account that the trap states may play a significant role, we should take into account these trap states, the formation of these traps. We should say that I should say that nowadays theoretical calculations have shown that indeed between valence zone and conduction band, there are few inner lying states which belong to the trap states of the quantum dots. And the formation of these trap states depends on the quantum dots itself and depends on some organic molecules which are attached to the quantum dots surface. So that's why we decided to find such levels, and okay, we found our deep analysis of experimental data permitted us to find such long-living and long wavelengths emission which belong to these trap states. And these trap states, the emission from these trap states is far from the main band position of the quantum dot photoluminescence, and the decay of this long wavelengths emission is 550 nanoseconds in comparison with the 10 or 15 nanoseconds of the main band. It means, on the basis of experiments, it means that in addition to the typical excitonic states in quantum dots, we should take into account some intermediate states which lie in between conduction band and valence band, is the so-called near band edge states and inter-gap energy states. Even when we investigated the single quantum dots, we found that the photoluminescence decays of this quantum dots is not mono-exponential. It means that even for a long quantum dots, we have the formation of dynamic trap states, which the number and position of which depends on the solvent polarity. And correspondingly, when we attach to porphyrin molecules, to quantum dots, we observe the multi-exponential decay. And this multi-exponential decay of quantum dots photoluminescence may be explained as a formation of trap states, which dynamically influence on the activation of quantum dots photoluminescence. Then we have carried out experiments at low temperature, and what we found, upon lowering temperature, we observed the increase. We observed the shift of the absorption and photoluminescence band to the blue, and we observed a specific kink of absorption band in absorption and a specific kink of photoluminescence. And when you should mention that this kink is observed far from the melting point or freezing point of solution. It means it is not connected with the changing of the matrix. It is connected with some surface processes which take place on quantum dot. So, and when we attach porphyrin molecules to quantum dots, we observe that this kink becomes stronger and more evident. It means that in this case, upon temperature lowering, we have the so-called phase transition of the capping ligand layer, which leads to the shift of the corresponding position of the corresponding states. It means that in this case, upon attachment of porphyrin molecules to quantum dots, and upon temperature lowering, we have the manifestation of few effects which influence of the gap on the gap of the quantum dot and influence of the formation of transformation of the ordering of ligand of capping ligands. So it means that temperature results have shown us that the capping layer plays also significant role in the formation of the intermediate case for quantum dots. So finally, for this quantum dots, we received very complicated system in comparison with simple quantum mechanical presentation. It means that in real case, when we have the quantum dots, we should take into account the formation of intra-gap states of various nature, and when we attach organic molecule like porphyrin to the quantum dot surface, we also observe the formation additional trap states, additional quenching states, and the complex. It means the quenching is complex in this case, and energy transfer takes place, but does not play the main role in the quenching process of our systems. This is results have been obtained for cadmium selenide quantum dots. Now, main conclusions in this case may be do the following. So spectral characteristics of quantum dot absorption bands reflect some specific crystal structure of quantum dots and reflects the very complicated physical processes which take place on the quantum dot surface. And photoluminescence properties of quantum dots may be explained or may be caused by a few reasons. It may be fine structure of states, intra-gap ligand-induced electron energy transfer. Then quantum dot energy state structure strongly influenced by low temperature transformation of capping ligand layer. And in fact, we have succeeded to separate energy transfer and other non-FRET processes. And these results should be taken into account when we are going to prepare some such systems for possible application in some biomedical investigation, especially when we are going to prepare, let's say, for instance, new agents for photodynamic therapy of cancer. So next part of my talk is connected with the results which have been obtained by probing of argentum indi as quantum dots by attached porphyrin molecules. But in this case, what we have in this case, interaction of quantum dot with porphyrin is have been realized via electrostatic interactions. What does it mean? So in this case, in addition to experimental results, we use the molecular mechanics in order to present what we have in hand, what quantum dot we have in hand, and we calculated, take it into account. We take into account crystallographic data of our quantum dot and sizes. We prepared the size of quantum dots. We have prepared the size of quantum dots according with experimental data. It means that we prepared quantum dot and put this quantum dot in solution and receive stable quantum dot of size which are very similar to the real size of quantum dots which have been obtained by using the other experimental methods. So after that, we realized the interaction of such quantum dots with porphyrin molecules via electrostatic interactions. It means glutathione molecules have a negative charge, and we prepared positive porphyrin molecule, and via electrostatic interaction, positive porphyrin molecule may interact with negatively charged quantum dots. So, and what we observed in experiment, we observed again when we attach porphyrin to quantum dots, we observed upon titration, we observed the rise of quantum of porphyrin absorption, one thing. Then we observed the strong quenching of photoluminescence of quantum dots. And in addition, we observed that the fluorescence lifetime remains unchanged. It means that the quenching process may be very fast, and what we observe, it might belong to the uncomplex quantum dots. So like in previous case, interaction of porphyrin with this type of quantum dots also leads to the quenching of photoluminescence of quantum dots. But in addition, we observe some specific effects. So here, this is upon titration, we observe the strong quenching of photoluminescence of quantum dots and appearance of photoluminescence of porphyrin molecules. And interestingly, that we observe some specific changes in absorption of porphyrin molecules. It means that we put in solution free base. This is blue curve. And upon interaction with quantum dots, we observe the changing of the spectra. From our experience, we know that it is connected with the formation of metal complex of porphyrin. So it means that upon attachment of porphyrin free base with such quantum dots, we have the metallation of porphyrin molecules. It's a very interesting result which possess us few interesting conclusions that we have. In reality, we have the formation of complex, and we have some surface chemistry which leads to the formation of metal complex on the surface, on the quantum dot surface. So the formation of metalloporphyrin in this case have been detected using the Raman spectroscopy, and we observed that in this case, okay, we have the formation of porphyrin molecules with silver central atom, which this silver central atom penetrates into the center of porphyrin molecules from the quantum dot shell. So, and detailed analysis of results of the titration of quantum dots by porphyrin molecules permitted us to say that we have analysis of these results permitted us to say that we have the specific formation of electrostatically interacting moieties. We have the formation of the complex of quantum dot with porphyrin molecules with a specific changing of the quantum of the porphyrin properties. So it means that at the first stage, upon electrostatic interaction of porphyrin molecules, we have the electrostatically coupled complex of quantum dot with free base. And the next stage, zinc ion may be penetrated into the center of quantum dot, in the center of porphyrin molecules, and we have the formation of zinc complexes of coupled porphyrin to the quantum dots. So we have the formation of such electrostatic conjugate containing zinc porphyrin mole. And the next step is the transformation, is the displacement of this zinc porphyrin into the specific place of the specific facet of quantum dots, which reflects the additional extra ligation effect of zinc atoms of porphyrin molecules. Concluding, I should say that these results, step by step, permitted us to prepare the picture how it's possible to receive such complex in this case. We have the sequential steps of the complex formation. And the first step, we have the interaction of quantum dot with porphyrin free base. As it realized via diffusionally controlled electrostatic interactions. The absorption band of this free base is shown by blue line. Then, after attachment, we have the formation of electrostatic conjugate, and in this electrostatic conjugate, we have the metal exchange. It means that in the porphyrin, in the free base, we have the formation of a zinc complex. This is the line. In this case, we have magenta spectrum. And finally, we have the reconstruction of the quantum dots by means of that porphyrin additionally interacts with the open facet of quantum dots, leading to the formation of the extra ligated zinc porphyrin molecule on the quantum dot. So after receiving all this specific information, how we have the information of this complex, and we know the details, what interacting species are formed in this case, we have the possibility to calculate, to estimate all necessary distances between interacting moieties in order to explain what is the reason of the quenching in our case. So here I present all these results, what we have, and after that we could calculate the overlap integral in this case, and finally we could estimate the critical distance of energy transfer, and finally we calculated the first transfer times in this case. And now we understood why we observe the strong quenching of photoluminescence intensity without changes of photoluminescence decay. It is connected with the situation that quantum dot photoluminescence quenching by one zinc porphyrin molecules is very fast and realized within picosecond time scale even, in comparison with 400 nanoseconds of initial fluorescence lifetime of quantum dots. It means that such complex analysis of experiments and using the theoretical formation of such interaction permitted us to fully explain all properties of such conjugated systems. So, and that I should say that processes which connect with the complexation with zinc penetration are very quick, and they realize that within the few seconds after preparation of our complexes. So I should say that we take these results, we have received these results in cooperation with our German colleagues, Ukrainian colleagues, and Russian colleagues. So, and our last results have been presented in few publications and in a few books and monographies. So, and of course, we received some foundation from national government as well from international projects, including Volkswagen, DID, and BearComp program. Okay, so thanks for your attention.
Thank you, Dr. Edward, for your very informative speech. It was really informative.
Yeah, thanks a lot. So I have had some talks, but to my mind, they are more how to say, they are more industrial or more applicable in comparison with my talk.
Yeah.
My talk concerns the basic ideas, how to understand what happens in such nano composites before using them in nano devices, of course. So I guess it's necessary step, but everyone should take and use his own way what we should do. Okay,
yeah, like it was easily understandable and really informative. Yeah.
No, thanks. I'm glad to be invited. So is it Lucy?
No, actually Lucy is not
your promoter.
My name is Jessica.
Okay,
I'm Jessica
of this discussion. Okay, thanks for your help. You immediately helped me to install my PowerPoint presentation. Okay, thanks. Good luck.
Thank
and
you.
how to say, think positive and be negative with respect to coronavirus. Yeah.
Yeah, that's
Yeah.
correct. That's all
Yeah.
we'll have to see to it. Yeah. So
Yeah.
yeah, thank you. And do we have any questions for Dr. Edward for the
No, okay, fine.
presentation?
Again, I should say many thanks, organizer,
Yeah.
for such presentation. In fact, I have, how to say, I have practice with my students here in Minsk.
Yeah.
Within a few months, I delivered lectures using the PowerPoint presentation, using the other platform, Microsoft Teams. But it's not so surprising for me. But nevertheless, it's a good experience, I guess.
Yeah.
Yeah.
Thank you. Thank you for
Thank you.
words.
Thank you
Yeah.
for your attention. Thank you. Yeah. Thank you.
Thank you. So as of now, for the next presentation, we have two presentations left, but the two of them are not available right now, so we couldn't
Because
connect
we
to them
started
as of
a little
now.
bit earlier. Yeah. Okay. Yeah. Mhm.
Yeah, at the schedule and also for the time difference. So I guess we'll have to wind up for today and we'll see to it that they'll have the presentations tomorrow. And we have a mail from Dr. Maria Mavri that is for the last presentation. Like if anyone is interested to get the presentation, like the PowerPoint presentation, then we will send an email to you. And if you're having any query from that, you can mail them directly. So this is all for today. So in any case, if anyone is having any queries, you can please let us know, or we can meet tomorrow at 11 a.m. for the same, like for the USA timings, East EDT. I hope that's all for today then. If there are any questions, please do let us know. Or you can also send us a message through the chat option over here if you're having any questions. So we'll also send you all the email IDs of all the presenters today. If you are unable to ask them in today's webinar, you can also mail them their queries. So once the webinar is over, like by tomorrow, we'll definitely give you all the details. So yeah, I guess that's all for today. So we'll definitely hope to see you tomorrow at 11 a.m. at this time. Thank you all for your presence and also for your support today. So we'll see you tomorrow at 11 a.m. in USA timings. Thank you. So I'm going to end the session and all the recordings will be provided to you after the conference. Like once the commencement of the webinar tomorrow, we'll be sending you all your certificates, your recordings and everything to your email IDs for sure. Thank you. We'll see you tomorrow.